Hi everyone and welcome to part 2 of my video playlist about the conversion of alkenes into epoxides. This video is about the epoxidation of allylic alcohols and related compounds, for instance allylamines. Because some epoxidizing reagents or catalysts can coordinate to hydroxy groups, allyl alcohols can often be epoxidized with exceedingly high stereoselectivity. With the aid of readily available, inexpensive titanium tartrate complexes, allyl alcohols can be converted into enantiomerically enriched epoxides or into enantiomerically enriched allylic alcohols by kinetic resolution. Depending on the oxidant and catalysts used, the transition state of such epoxidations will vary, but essentially it is the formation of a hydrogen bond to the hydroxy group of the allyl alcohol what controls the stereoselectivity of these reactions. Allylic alcohols are more difficult to oxidize than the corresponding non-hydroxylated alkenes, due to the inductive effect of the oxygen atom. Therefore, the rate of epoxidation of hydroxycyclohexene by peroxy acids is lower than that of cyclohexene. Nevertheless, the hydroxy group can form a hydrogen bond with the oxidant, what again increases the rate of epoxidation of hydroxycyclohexene, if for instance compared to the epoxidation of methoxy or acetoxycyclohexene. This hydrogen bond with the oxidant also increases the diastereoselectivity of the epoxidation and strongly favors a cis epoxidation in the case of hydroxycyclohexene. Allylic ethers, on the other hand, preferentially yield trans epoxides. This cis selectivity can be further enhanced by using a hydroperoxide and catalytic amounts of a vanadium or titanium complex. Interestingly, when increasing the ring size of allylic hydroxycycloalkenes from 6 to 8, the diastereoselectivity of epoxidation with peroxy acids changes from cis to trans, while the catalyzed epoxidations remain cis-selective. Epoxidations of allylic alcohols with hydroperoxides catalyzed by early oxophilic transition metals such as titanium, vanadium or tungsten also proceed much faster than epoxidations with peroxy acids. Thus, as shown on a previous slide, hydroxycyclohexene is epoxidized by peroxybenzoic acid at half the rate of cyclohexene. Epoxidation of cyclooctanols with terz-butyl hydroperoxide and 1% of a vanadium complex proceed 1000 times faster with the allylic alcohol than with the octanol with 3 carbon atoms between oxygen and the olefin. Because hydroperoxides are weak acids only, allylic alcohols can thus be epoxidized effectively and with high selectivity under exceedingly mild reaction conditions. Let's now check some specific examples. The increased rate of epoxidation of allylic alcohols by hydroperoxides discussed on the previous slide can be used to perform selective monoepoxidations of polyenes, as shown here. Despite the high reaction temperature, only the allylic alcohol was epoxidized. This is a typical enantioselective epoxidation of an allylic alcohol with terz-butyl hydroperoxide and a catalytic amount of titanium tartrate, as developed by the Sharpless group. Again, the allylic alcohol was epoxidized faster than a tri-substituted alkene. Indoles, which are electron-rich and readily react with most oxidants, may remain unchanged during Sharpless epoxidations. In this and the previous example, the epoxidation already proceeded at -20 degrees Celsius and gave a high yield of the expected epoxide. This is an example of enantioselective Sharpless monoepoxidation of a diene with cumyl hydroperoxide and a titanium tartrate. These oxidations often give high yields and enantioselectivities, but in this instance twofold epoxidation was probably a competing side reaction. Allylic alcohols can often be epoxidized selectively in the presence of electron-deficient alkenes, as in this example. Despite the excess of peroxy acid, only the allylic alcohol was oxidized. Tertiary alcohols do not form hydrogen bonds as readily as primary or secondary alcohols and are therefore less effective at directing regio- and stereoselectivity of epoxidations. Steric bulk may further slow down the rate of epoxidations of tertiary allylic alcohols. Here, for example, the tri-substituted alkene reacted faster than an allylic alcohol. In this example, a brominated cyclohexadiene could be epoxidized selectively with MCPBA, depending on which hydroxy group was silylated. Such selectivities are difficult to predict correctly and must be determined experimentally. Unlike the previous example, here the halogenated CC double bond was epoxidized more slowly than the allylic alcohol because of the enhanced rate of sharpless epoxidations if compared to epoxidations with peroxy acids. Here a kinetic resolution of an enol carbamate was attempted, but no high enantioselectivity could be achieved. Again, the allylic alcohol reacted faster than the enol carbamate. One potential problem during ketone epoxidations is Baeyer-Williger oxidation. In parts 1 and 3 of this video playlist, there are some examples where ketones were converted into esters. This side reaction can, however, be suppressed by avoiding an excess of oxidant and by keeping the reaction mixture neutral or slightly basic. In this example, despite the excess of MCPBA and the long reaction time, no significant amounts of ester were formed. In this example, a sharpless epoxidation was performed with a simple, unconjugated ketone, and a high yield of the expected epoxide resulted, without any oxidation of the ketone. The starting diol of this example contained 2 allylic alcohol substructures, but one of them was electronically deactivated by a keto group. Unexpectedly, with MCPBA alone, an almost equimolar mixture of 2 diastereomers resulted. When 1% of a manganese complex was added, the diastereoselectivity of the epoxidation was enhanced, but surprisingly, the trans epoxide became the main product. Even aldehydes sometimes remain unchanged during epoxidations, as in this example. Admittedly, this aldehyde was rather unreactive, but a large excess of oxidant was used. Also, the acetal and keto groups remained intact and the desired epoxide was obtained in 71% yield. Diastereoselectivity was poor, however. Even this more reactive aldehyde could be epoxidized without oxidation of the formyl group, despite the huge excess of hydrogen peroxide. The solvent DMF, which is also easy to oxidize, may have acted as protecting agent. Amines also react with most epoxidizing reagents, and epoxidations of alkenylamines work usually best under acidic conditions. In this example, such an epoxidation succeeded without any additional acid, but less than 1 equivalent of MCPBA was used. MCPBA is a weak acid only, with a pKa of 7.6, and will only partially protonate most aliphatic amines. Here, the amine was protected by protonation with trifluoroacetic acid, and a fair yield of the required epoxide was obtained. In this example, a Bock-protected allylamine had to be epoxidized. Best results were achieved with a huge excess of oxone in acetone, probably by intermediate formation of dimethyl dioxyrane. The diastereoselectivity was poor though. Bock protection was sufficient to prevent oxidation of the amino group. Here, a tertiary allylic amine was protected as ammonium trichloroacetate, and the epoxidation was performed with an excess of MCPBA. In this instance, the diastereoselectivity was high, but tricky to predict correctly. If you find this confusing, you're right, it's a bit confusing. I would also have expected the other diastereomer. Most textbooks suggest that stereo and chemoselectivity can be predicted, but the reality is that each new starting material or slight variation of the reaction conditions can give unexpected results. The rigorous determination of the structure of new products with all available means is therefore imperative. Not all acids are suitable for the protection of amines during epoxidations. A large excess of a weak, highly nucleophilic acid can cause ring opening of the newly formed epoxide, as in this example. Here, 5 equivalents of toluene sulfonic acid were added to the starting allylamine, and upon epoxidation with MCPBA, mostly a tosylate was obtained. With the less nucleophilic tetrafluoroboric acid, no epoxide but only a diol resulted, again with high diastereoselectivity. Interestingly, the epoxide could be obtained by treatment of the tosylate with a base, but the overall yield was low. A better option may have been to use less acid and a more reactive oxidant. This is again an example of the epoxidation of an allylic amine without any added acid. Surprisingly, despite the large excess of hydrogen peroxide, no amine oxide was formed. If a non-nucleophilic acid is used to protect amino groups from oxidation, other nucleophiles present in the reaction mixture may be alkylated by the epoxide. In this example, a benzyl ether was prepared by alkylation of benzyl alcohol. The epoxidation proceeded with high diastereoselectivity, and only one of the 2 possible regioisomeric ethers was formed. Let's have a look at some typical side reactions. You can find a more detailed discussion of side reactions in the first video of this playlist. The strong oxidants required for epoxidations may also oxidize other functional groups. For instance, amines, thioethers, sulfoxides, aldehydes, acetals or phenols. In this example, a tertiary allylic amine underwent almost complete oxidation upon treatment with 1 equivalent of MCPBA for 5 minutes. Such oxidations can sometimes be prevented by converting the amine into an ammonium salt. Acidic reaction conditions may prevent the oxidation of amines, but can also cause the isomerization, elimination or etherification of allylic alcohols. Many epoxidations fail because the epoxide is too unstable and rearranges into a ketone or aldehyde. Other potential side reactions include allylic oxidation, Baeyer-Villiger oxidation of ketones and aldehydes, the oxidative cleavage of alkenes, and dehydrogenations. Tertiary CH groups are sometimes hydroxylated by dioxyranes or peroxy acids under surprisingly mild conditions. Here, for example, half of the starting material was hydroxylated at 0 degrees Celsius, and a secondary alcohol was partially oxidized to a ketone. Here is a short selection of some further, mostly recent examples. You can also find this reference list in the description of this video. Part 3 of this playlist is about the epoxidation of electron-deficient alkenes. These often require different conditions than electron-rich alkenes, and I'll show you several examples of selective epoxidations of multifunctional alkenes. So long.